Welcome. Thank you for joining us today for this technical overview. We are here to explore the Client's Guide to RAT Token Authority, which serves as a definitive blueprint for establishing service-to-service trust. In modern distributed architectures, securing communication between internal services is a critical challenge. This session will detail how RAT Token Authority facilitates seamless authentication and authorization, providing the foundational security required for a robust and trustworthy ecosystem. Let's dive into the core principles and implementation strategies. In a distributed microservice architecture, we must operate under the assumption that the network is inherently hostile. This leads us to the fundamental principle of zero trust, which dictates that we never trust and always verify every single interaction. This approach is built upon three critical pillars: identity, authorization, and integrity. First, we address identity. In a zero-trust environment, we cannot rely on network location for security. We must ask, how does a service prove it is truly who it claims to be? This requires robust mechanisms to authenticate the identity of every service making a request. Second, we have authorization. Establishing identity is only the first step. We must also verify permission. Even if a service is authenticated, we must determine if it is permitted to perform the specific action it is requesting. Finally, we have integrity. Beyond knowing who is sending a request and what they are allowed to do, we must ensure the data itself remains secure. We must constantly verify whether the request has been tampered with while in transit. By grounding our architecture in these three pillars, we create a secure and resilient foundation for our services.
Pasado is a secure-by-design token that allows us to move beyond JWTs by eliminating inherent design flaws. A critical vulnerability in JWTs is algorithm confusion, where the token itself dictates its own validation method. This flexibility creates multiple attack vectors, such as the alg-none exploit, the use of weak ciphers, or header confusion, all of which are depicted in the complex and risky validation flow on the right. Pasado addresses these issues by ensuring that the protocol version itself determines the cryptography. Because there is no negotiation involved, we eliminate an entire class of security vulnerabilities. In our environment, the Raw Token Authority issues Pasado v4.public tokens, which utilize strong, modern ED25519 signing by default. In contrast to the convoluted path of JWT validation, Pasado provides a straightforward, simple, and secure approach where the version dictates the security parameters.
RAY Token Authority is the centralized service designed to bring discipline to token management within zero-trust environments. To ensure the highest levels of performance and reliability, it is built on a modern stack, leveraging Rust, Axum, and Tokio. The service operates across three primary pillars. First, it handles token issuance by cryptographically signing Pasado version 4 public tokens. Second, it automates the entire lifecycle of ED25519 keys, including rotation, retention, and garbage collection. Finally, it enables verification by exposing a dedicated public key discovery endpoint at the /keys path, allowing clients to easily retrieve the necessary keys to validate tokens. This comprehensive approach ensures a secure, automated, and high-performance identity infrastructure. In the architect's view, establishing trust between services is paramount. We are examining two primary paths for a client service to obtain a secure token from the Raw Token Authority before calling a target service. How a client proves its identity to the authority depends heavily on the underlying infrastructure. The first pattern, which we call the fortress, relies on application-managed MTLS. In this scenario, the client application itself is directly responsible for managing its cryptographic identity. This approach is typical in on-premises data centers or environments without a service mesh. The second pattern, the alliance, utilizes infrastructure-managed MTLS. Here, the client leverages the inherent platform identity provided by a service mesh, such as Istio running on AKS. By offloading identity management to the infrastructure, teams can simplify application logic while maintaining a robust security posture. Pattern 1, titled The Fortress, introduces the concept of direct client authentication. In this model, the client application logic is directly responsible for building security measures to achieve maximum control over the authentication process. The primary mechanism used is application-level mutual TLS, or MTLS. The flow works as follows. First, the client application uses its private key and client certificate to initiate an MTLS handshake with the raw token authority. Second, the authority cryptographically verifies the client certificate to establish its identity, typically by inspecting the certificate's common name. Once the identity is successfully proven, the authority issues a short-lived, scoped Passeto token back to the client. This approach ensures that security is tightly integrated within the application layer itself. This slide breaks down the operational logic of the Fortress pattern, specifically detailing the workflows for both the client, Service A, and the verifier, Service B. On the left, the client workflow begins with Service A loading its client certificate and private key. It then initiates a mutual TLS connection to the internal RA token authority. Once the identity of Service A is established via MTLS, it requests a Passeto token, explicitly setting the audience to Service B. After the authority issues the token, Service A includes it in the authorization header for its final API call to the target service. On the right, we see the verifier workflow from the perspective of Service B. When the request arrives, Service B extracts the Passeto token from the header. It then communicates with the RA token authority to fetch the necessary public keys via the /keys endpoint. These keys are typically cached to minimize latency. With the public key in hand, Service B performs the critical verification steps, checking the cryptographic signature, ensuring the token has not expired, and confirming that the audience claim matches its own identity. Once these checks are successful, access is granted to the underlying resource. In this second pattern, titled The Alliance, we focus on the concept of trusting the infrastructure. By utilizing a service mesh, such as Istio on AKS, we can offload transport security and identity verification to the platform itself. This allows developers to greatly simplify their application code by removing these complex requirements. The core mechanism involves a sidecar proxy, such as Envoy, which manages mutual TLS automatically. Through this mesh, every workload is assigned a cryptographic identity based on the SPIF standard. The operational flow consists of 3 key steps. First, the client service authenticates to the raw token authority using its mesh-provided identity, which is typically a projected Kubernetes service account token. Second, the authority validates this platform-level identity. Finally, once validation is successful, the authority issues the Passeto token. As illustrated in the diagram, while the application within the Kubernetes pod communicates via plain text HTTP to its local sidecar proxy, all external communication to the token authority is secured via mesh-managed MTLS, ensuring a secure and verified connection. In the alliance pattern, the client and verifier logic ensures a secure and decoupled communication flow. Starting with the client workflow for Service A, the process begins when the client app reads a projected service account token from the local file system. This token is then transmitted via an HTTPS call to the raw token authority. The authority validates the identity and issues a Passeto token in return. Armed with this token, the client app makes its final API call to Service B, placing the Passeto token in the authorization header. Notably, while the application manages the token, MTLS is handled transparently by the sidecar. On the right, the verifier workflow for Service B remains remarkably simple because the verification logic is identical to that used in the Fortress pattern. This consistency is intentional. Passeto provides a uniform authorization layer that operates independently of the underlying transport security mechanism. This decoupling is a core architectural benefit, allowing security policies to remain stable even as the infrastructure or transport protocols evolve. In this side-by-side comparison, we analyze 2 distinct strategies for implementing client security: the Fortress, representing direct MTLS, and the Alliance, representing the service mesh approach. Starting with the identity source, direct MTLS relies on client certificates, while the service mesh utilizes SPIF IDs or Kubernetes service accounts. This leads to a fundamental difference in how transport security is managed. In the Fortress model, security is integrated directly into the application code, whereas the Alliance offloads this responsibility to the infrastructure through a sidecar. As a result, code overhead is significantly higher for direct MTLS due to the complexities of TLS configuration and certificate management. In contrast, the service mesh allows for a simple HTTPS call, drastically reducing the burden on developers. This automation extends to key management, which is handled natively by the service mesh compared to the manual or external tooling required by the Fortress. When considering the ideal environment, direct MTLS is the preferred choice for on-premises or legacy systems without mesh support. However, for modern Kubernetes-based stacks, such as AKS with Istio, the Alliance model is the standard. In terms of authorization granularity, the Fortress approach enables checks based on both service identity and application data, while the Alliance focuses on service identity by default. Importantly, the underlying authorization logic remains identical across both architectures, with both utilizing Poseidon verification to maintain a consistent security posture. Think of the token as a portable, tamper-proof passport for authorization. Regardless of the underlying pattern, a Pasitoto token serves as a rich container for essential identity and access data. First, let's look at granular authorization via custom claims. By using an application-aware token authority, we can embed deep business context directly within the token. This allows us to answer more than just who is calling. It identifies which entity they represent and precisely what permissions they possess. In the illustration, you can see how claims like tenant ID, user level, and specific scopes are bundled together to provide a complete picture of the requester's authority. Second, we have security through implicit assertions. To mitigate the risk of replay attacks, an assertion can be included during the signature calculation while remaining absent from the transmitted payload. This technique binds a token to its intended context, such as a specific internal API version, ensuring that a token meant for one service cannot be maliciously reused against another. This results in a highly secure and context-bound authorization mechanism. For any service acting as a verifier, establishing trust is paramount. This requires consistent access to public signing keys. Our Ray Token Authority simplifies this by exposing a JWKS-like endpoint at /keys for key discovery. To achieve high performance, we recommend a 3-step implementation strategy, as shown in this diagram. First, the client service fetches the set of public keys from the /keys endpoint immediately upon startup. Second, it caches these keys in memory to avoid the overhead of a network call for every single token verification. Finally, the service performs a periodic background refresh of the cache. This allows for seamless, automated key rotation, ensuring that tokens are always verified against the correct keys without any interruption to the service. The Ray Token Authority is engineered for production-grade reliability, incorporating architectural features that ensure robust operation under pressure. Our fail-safe design is built upon 4 critical pillars. First, we utilize validated configuration. The system is designed to fail fast at startup if it detects invalid environment variables, preventing the risks associated with unpredictable runtime behavior. Second, we have implemented graceful shutdown capabilities. When a SIG term is received, the authority stops accepting new requests while allowing all in-flight operations to complete successfully. Third, global rate limiting protects the system against traffic overload and potential abuse, ensuring consistent performance. Finally, we maintain rich observability through structured, correlative logging and comprehensive Prometheus metrics. These tools provide the deep operational insights necessary to monitor health and maintain the high standard of resilience required for this authority. Our architectural principles are defined by 4 primary pillars. First, we verify identity first, utilizing the strongest mechanisms available, such as MTLS for direct connections or platform identity through SPIF in a service mesh. Second, we issue trust by minting short-lived, scoped Poseidon tokens that provide a rich, application-aware authorization context. Third, we ensure we validate always. The receiving service is required to cryptographically verify the token's signature, expiration, and audience claim before access is granted. Finally, we leverage the platform by intelligently utilizing the capabilities of the underlying infrastructure. By offloading transport security to the platform, such as through the Alliance, we significantly reduce application complexity while maintaining a robust security architecture. To summarize the key takeaways from our discussion, RAT Token Authority provides a modern, secure-by-design foundation for service-to-service trust. By utilizing Poseidon, it eliminates entire classes of vulnerabilities common to traditional JWT implementations. When considering architectural approaches, the Fortress pattern, which relies on direct MTLS, is the ideal solution for environments where applications must manage their own transport security, such as on-premises or non-mesh deployments. Conversely, the Alliance pattern is the superior default for cloud-native environments like AKS with Istio. This pattern leverages platform identity to significantly simplify application code. Ultimately, from the client's perspective, the objective remains consistent across any architecture: to prove identity in order to obtain a portable token that enables fine-grained, application-aware authorization.